Okay, so I'm Gavin Bailey. I'm the head of business development at Aimsun for the UK and the Nordics. I'm going to talk to you about traffic digital twins, giving a bit of an update on our previous presentation and work with Tees Valley, which we started earlier this year. So just as a recap, what is a traffic digital twin when we're talking about it from Aimsun's perspective? It's a digital replica of the road, pedestrian, cycling infrastructure connected to real-world sensors and automatic traffic counters. These can be a range of sensors like scooter mover detectors, which specifically are induction loops in the road, which capture the absolute count of vehicles moving over them in real time. It can be computer vision based traffic detection technologies using dedicated cameras or CCTV like Viva City. And it can also be mobile phone or in-car data, which is termed as floating vehicle or floating car data. So this is typically capturing a sample of the vehicle population moving through the network. We take that data and we put it into the digital replica to represent the traffic in real time. There's some latency in communication of the information, but we aggregate the traffic data up to 5-minute time slices to provide a kind of up-to-date view of what's going on the network. We also provide predictions on what's likely to happen on the network up to an hour in advance based on a rolling time horizon. That's using AI-driven analytical predictions and also simulated traffic simulation predictions. These can be deployed at any scale from junction to corridor to a city, regional and national scale. The main application for these is for monitoring and observation of the traffic network and traffic state on the network, and actuating change on the network through our systems using AI-driven and simulation-driven decision support. So with Tees Valley, when we build a digital twin, we start with the data, always look at the data and the health of that data and seek to normalize it and improve it. Here you can see a sample of the detector data from the Tees Valley network. All the detectors are down on the left, and then we've got the data for every single day of the year for those each of those detectors. Black is very bad or no data at all. Red is poor quality data. Green is the best quality data. Here you can see that they've got a fair amount of green, but there's a large number of gaps in the data. So what we do is we use AI-driven statistical techniques to interpolate and impute values to essentially clean the data and uplift it and enhance it to a usable state. If after this process the data is still somewhat lacking, we'll then advise the client on the best locations to kind of deploy new detection infrastructure or to purchase targeted floating vehicle data to improve the situation. Here you can see the patterns from that data for Tees Valley, and this is particularly useful. So this is used this is used as a reference information or reference data for the machine learning algorithms for the purposes of driving prediction and understanding what normal looks like on the network or for any given detector. What we do is we deploy a machine learning pattern generator onto that data set to identify daily trends in traffic across detectors and for the whole network. So on the left, you can see that it's identified a number of patterns. You can see the early morning peak, the morning peak and the AM and the PM peak. And then for some of the patterns, kind of a bit of an interpeak, which tends to be weekends. The really interesting insight from this data, which talking to some consultants that work in the Tees Valley area on traffic models for the purposes of planning, is that we see Friday, Saturday, and Sunday being distinct days. Typically, it's not uncommon to see Saturdays and Sundays as distinct days across the whole year, but it's maybe less common to see Friday as a distinct day. There was also an expectation with the consultant that Monday would be a distinct day given the expected change in travel habits due to COVID, but in Tees Valley that doesn't seem to be the case. So we can derive some really useful and interesting insights, not just for the purposes of the digital twin, but also for the purposes of traffic planning and management. So the system in Tees Valley focuses on two core functionalities: the incident detection module and bus reliability. The incident detection module is an AI-driven module which identifies anomalies in traffic flow over detectors. So here you can see in the simulated anomaly that there's been a significant drop of traffic. It's actually gone to 0 over this detector, so there it assumes that there's an incident upstream from it. It can also flag an incident if the traffic flow drops outside of the expected range for the day. Once identifying the incident, an operator can go into the system and they can manage the traffic, the network accordingly. Here they can select from pre-established response plans. They can run up to 4 response plans, 1 do nothing and 3 do something. The results are presented visually here in the form of a heat map, and they can hop through for the next hour to see how the traffic evolves based on the management of that incident. The results are presented numerically in tabular form and also graphically for easier and quick identification of the most appropriate plan. All of this can be automated if the authority chooses to do so. In this particular incident, you can see that the do nothing, which is the top left, is actually the most appropriate action here. So it's a really valuable tool in identifying whether no action is actually the best action. The other core functionality for this system, as I said, was bus reliability. This works in a similar fashion to incident detection, but is connected to live bus data. So we take the live location of buses and we basically compare it to where it should be based against the bus timetable. This can then be used to identify a late bus, and then it can go through a similar process with the incident detection, automatically identifying the most appropriate response plan and quantifying the impacts of that, whether that be on intersecting bus routes, causing unwanted delay, or significant unwanted delay and congestion across the network. This particular part of the system we're actually in the process of implementing and deploying. We expect that to be fully deployed and implemented in January next year. So where next? As I said, the automated bus reliability is the next focus for this system. The incident detection is up and running, but it's going through its kind of training period. So we expect by September it should be fully trained and kind of up to scratch on what it might expect to be the norm for the network. The thing that I really want to impress upon with these tools, with these digital twins, is that they are tools and they can be applied to a multitude of situations, such as air quality management in Oxfordshire, which we did in 2019, evacuation management and analysis in China. It can be used for planning and management of new modes, such as connected and autonomous vehicles, freight, the freight sector, and it can also be used for roadworks assessments in kind of pre-planning non-real-time applications. That concludes my presentation. Thank you very much.
So next question, please, if I could, is to Gavin, is patterns of count for different types of days. What are the different types? How did you choose the different types?
So the patterns are automatically generated from by a machine learning pattern generation algorithm. So those are automatically generated patterns identified from the data based on trends that it sees. The patterns are then allocated to, so we look at each detector for the network, and those patterns are allocated to the detectors for each day of the year based on what it's how they match, basically. So it automatically identifies the patterns and then it will match those. So it's all what you're seeing on screen is emergent from data rather than a trained planner going and actually allocating the patterns. What we do though is so sometimes the algorithm can identify countless numbers of patterns, and we will go through a process of then condensing them down to more sensible patterns. But that's kind of becoming rarer and rarer as the algorithms are used more and more and see more data. I don't know if that one is the question, but
that's good. Thank you. Our link's second question, if I could, Gavin, is how does your model look to offer other modes of transport to customers when buses are compromised by local traffic congestion?
That's a good question. So the model itself is a situational awareness tool and a management tool for traffic operators and traffic managers. So at the moment, in its application, it would be for a traffic manager to allocate an alternative mode. At the moment, what we are seeing in the industry is that there's actually a lack of data in terms of live data for other modes that are available, say active travel modes. Or independent kind of on-demand modes. If that data is available, we can put it in the model and then we can set up automations to optimize that to make recommendations. But at the moment, we're a bit limited by the data that's available in the market that is purchased or owned by authorities.